Derivation from Lorentz force. The force on a single conductor in a magnetic field is given by the Lorentz law. F equals B times L times I, where B is the magnetic flux density Tesla, L is the length of the conductor inside the field meters, and I is the current through the conductor ampere. In a DC motor, the armature consists of many such conductors arranged on a rotating cylinder, the rotor. Each conductor experiences a force that is tangent to the circle trying to push the rotor around. F total equals Z divided by 2 times B times L times IA. The division by 2 appears because only half of the conductors are on the active side of the magnetic circuit at any instant. T equals F total times R equals Z divided by 2 times B times L times R times IA. The product BLR is the magnetic flux phi linking one turn of the armature winding Webers. Ray writing gives the classic torque equation. T equals KT times phi times IA, where KT equals Z divided by 2 for a simple lap wound machine. This derivation shows that torque comes directly from the interaction of current-carrying conductors. With a magnetic field, exactly like a child pushing a swing, the harder you push, more current, or the stronger the wind, more flux, the larger the swing torque. Practical example. For a motor with 200 conductors, Z equals 200 and a radius of 0.05 meters, a magnetic flux density of 0.4 Tesla, conductor length inside the field of 0.03 meters, an armature current of 3 amperes, the torque is T equals 200 divided by 2 times 0.4 times 0.03 times 0.05 times 3 equals 18 Newton meters. This calculation demonstrates how each physical parameter contributes linearly to the final turning effort. Fundamental torque formula. T equals KT phi IA dash term definitions and units. T dash torque Newton meter. Nm, it is the turning effort analogous to the twist you feel when using a wrench. KT dash torque constant Newton meter per Weber ampere, Nm per Weber ampere. It tells how efficiently the motor converts the product of flux and current into turning force. Think of it as the gear ratio inside the motor that scales electrical effort to mechanical effort. Phi dash magnetic flux per pole, Weber, Wb, it is the amount of magnetic field line stuff that cuts through the armature winding. In everyday terms, increasing phi is like making the magnetic field stronger, similar to turning up the strength of a magnet that pulls a metal toy car. IA dash armature current, ampere, A, this is the current flowing through the rotor windings. More current means more electrons pushing on the magnetic field, just like pressing harder on a bicycle pedal. Unit check. KT Newton meter per Weber ampere times phi Weber times IA ampere equals Newton meter, confirming the equation is dimensionally correct. Practical illustration. If a motor has a torque constant of 0.05 Newton meter per Weber ampere, a flux of 0.02 Weber, and carries 10 amperes, the torque becomes T equals 0.05 times 0.02 times 10 equals 0.01 Newton meter. Even a modest flux and current can generate a noticeable torque when the constant is appropriately sized. Explanation: how to calculate and interpret the torque constant, K sub T. For a given motor geometry, K sub T can be found from its construction data or measured experimentally. Using the derivation above, K sub T equals Z over 2 when the flux phi is defined as the flux linking one turn. In SI units, K sub T is expressed as Newton meter per Weber per ampere. If a motor has 100 conductors, Z equals 100, then K sub T equals 50 Newton meter per Weber per ampere. This means that for each Weber of flux and each ampere of armature current, the motor produces 50 Newton meter of torque. Experimental method: spin the motor at a known speed. Measure the back EMF to determine phi, since E sub B equals KE phi omega and KE equals KT in SI. Apply a known current and read the torque with a dynamometer. Then solve K sub T equals T divided by phi IA. Interpretation: a larger K sub T indicates a motor that can produce more torque for the same electrical input, ideal for high-load startup applications such as electric vehicles or robotic arms. Example: a motor with phi equals 0.015 Weber and IA equals 8 amperes produces 6 Newton meter of torque. Its torque constant is then K sub T equals 6 over phi times 8 equals 50 Newton meter per Weber per ampere. This matches the value expected for a machine with roughly 100 conductors. Explanation: effect of changing magnetic flux phi linear versus saturation. In the linear region of the magnetic circuit, phi increases proportionally with the field current or magnetizing ampere turns. Thus, doubling phi doubles the torque assuming I sub A stays the same. This is similar to turning up the volume on a speaker. The sound gets louder in direct proportion. However, as the iron core approaches magnetic saturation, the relationship bends. Large increases in magnetizing current produce only small increases in phi. In the torque equation, this means the torque no longer rises linearly with field current. The motor will reach a flat spot where adding more field current yields little extra torque. Just like trying to push a stuck door harder does not make it open once you have reached the maximum friction. Design implication: engineers choose a flux level that stays in the linear region for the required operating range, or they deliberately use saturation to limit torque at high speeds field weakening. For instance, a traction motor may run at high speeds with reduced phi to keep the back EMF below the supply voltage, sacrificing torque but allowing higher RPM. Numerical illustration: suppose a motor's flux versus field current follows phi equals 0.02, I sub F up to I sub F equals 5 amperes linear. At I sub F equals 5 amperes, phi equals 0.10 Weber. Beyond that, the core saturates and phi only increases to 0.12 Weber at I sub F equals 10 amperes. If K sub T equals 30 Newton meter per Weber ampere and I sub A equals 6 amperes, torque at 5 ampere field current is T equals 30 times 0.10 times 6 equals 18 Newton meter. Whereas at 10 ampere field current, it is only T equals 30 times 0.12 times 6 equals 21.6 Newton meter, a modest increase despite doubling the field current. Deriving the torque speed straight line. The mechanical power balance of a DC motor is P equals T omega, where omega is angular speed, radians per second. The electrical side gives V equals E sub B plus I sub A R sub A with back EMF E sub B equals K sub E phi omega. Solving for I sub A and substituting into T equals K sub T phi, I sub A yields a linear relation between torque and speed. T equals T sub stall minus open parenthesis T sub stall divided by omega, no load close parenthesis omega. T sub stall is the torque when the motor is locked. Omega equals 0, equal to K sub T phi I sub A stall. Omega no load is the speed when no torque is produced. T equals 0, found from omega no load equals V divided by open parenthesis K sub E phi close parenthesis. The equation draws a straight line from the stall point on the vertical axis down to the no-load speed on the horizontal axis, just like a seesaw that tilts linearly from one end to the other. This characteristic helps us predict how much torque a motor will give at any speed. Slope interpretation. The slope negative T sub stall over omega no load is negative, meaning torque falls as speed rises, a fundamental trade-off in all motors. The steeper the slope, the faster the torque drops, indicating a motor optimized for high speed rather than high torque. Example calculation. A motor rated at 24 volts with K sub T equals 0.05 Newton meters per Weber ampere. Phi equals 0.02 Weber. An armature resistance R sub A equals 0.5 ohms has a stall current of I sub A stall equals V divided by R sub A equals 48 amperes. Stall torque is T sub stall equals 0.05 times 0.02 times 48 equals 0.048 Newton meters. No load speed is omega, no load equals V divided by open parenthesis, K sub E phi close parenthesis, equals 24 divided by open parenthesis 0.05 times 0.02 close parenthesis equals 24,000 radians per second. The torque speed line therefore is T equals 0.048 minus open parenthesis 0.048 divided by 24,000 close parenthesis omega. Suppose a small DC motor has flux per pole phi equals 0.02 Weber in the linear region. Armature current IA equals 5 amperes. Torque constant KT equals 25 Newton meter per Weber ampere. Using the basic torque formula, T equals KT phi, IA equals 25 times 0.02 times 5 equals 2.5 Newton meter. Interpretation: the motor can produce a turning force of 2.5 Newton meters. roughly the force needed to lift a 25 kilogram weight with a 1 meter lever, since torque equals force times distance. If the same motor runs at 1,500 revolutions per minute, omega equals 1,500 times 2 pi divided by 60, approximately 157 radians per second, and the supply voltage is 24 volts. The back electromotive force would be EB equals K E phi omega. With KE equals KT in SI units, EB equals 25 times 0.02 times 157, approximately 78.5 volts, which exceeds the supply. Consequently, the motor cannot sustain that speed at the given flux. It will enter field weakening mode and the torque will drop. This illustrates why designers must keep the product phi omega within the limits set by the supply voltage. Torque equations for different DC motor types. Separately excited, the field winding is powered from an independent source, so phi is constant regardless of armature current. Torque expression. T equals KT phi fixed IA. This is like having a fixed strength magnet that never changes. Shunt wound, the field winding is connected in parallel with the armature, so the same supply voltage appears across both. Field current is roughly constant, making phi nearly constant. Torque is still approximately KT phi IA, but now phi can be altered by changing the supply voltage. IF equals V divided by RF. T approximately equals KT phi IA. Compound wound, a combination of series and shunt fields. The total flux phi equals phi shunt plus phi series. Since series flux depends on armature current, torque becomes T equals KT open parenthesis phi shunt plus KS IA close parenthesis IA equals KT phi shunt IA plus KT KS IA squared. This yields a quadratic term, giving higher torque at low speeds, good for starting heavy loads. An analogy is a car with both a turbocharger, speed-dependent boost, and a fixed ratio gearbox. Design implication. Separately excited motors provide the most linear torque control. Shunt wound motors are simple and self-regulating, while compound motors excel in applications that need high starting torque and reasonable speed regulation. Example comparison. For a motor with KT equals 0.4 Newton meters per Weber ampere and phi shunt equals 0.15 Weber, series coefficient Ks equals 0.1 Weber per ampere, and armature current of 10 amperes. Separately excited torque. T equals 0.4 times 0.15 times 10 equals 0.6 Newton meters. Shunt wound torque, same numbers. T approximately equals 0.6 Newton meters. Compound torque. T equals 0.4 times open parenthesis 0.15 plus 0.1 times 10 close parenthesis times 10 equals 0.4 times 0.25 times 10 equals 0.1 Newton meters, showing the extra boost from series flux. Mechanical power is the product of torque and angular speed. P equals T omega. Rearranging gives T equals P divided by omega. If you know the motor's rated power, say 500 watts, and its speed at that rating, 1500 revolutions per minute equals 157 radians per second, the torque at the rated point is T equals 500 watts divided by 157 radians per second, approximately 3.18 Newton meters. Conversely, if you need a certain torque, you can compute the required speed for a given power, or the required power for a desired speed-torque pair. This relationship is used in gearbox selection. A high-speed, low-torque motor can be paired with a gear reduction to increase torque while reducing speed, because the power stays approximately constant, ignoring losses. Practical use case. An electric scooter motor is rated at 2 kilowatts and 3,000 revolutions per minute, omega approximately 314 radians per second. The torque is T equals 2,000 watts divided by 314 radians per second, approximately 6.37 Newton meters. If a rider wants a higher hill climbing torque of 10 Newton meters, the motor must either increase power, for example 3 kilowatts, or be run at a lower speed via reduction gear that brings the speed down to omega equals 2,000 watts divided by 10 Newton meters, equals 200 radians per second, approximately 1,910 revolutions per minute. Key insight: torque and speed are inversely related for a fixed power output. Increasing one necessarily reduces the other unless additional power is supplied. Explanation: typical exam questions and short answers. Derive the torque equation starting from the Lorentz force. Show F equals BLI. Sum over all conductors multiplied by rotor radius, replace BLR with phi and obtain T equals KT phi I. If a motor has KT equals 30 Newton meter per Weber ampere, flux phi equals 0.015 Weber and armature current 8 amps. Calculate torque. T equals 30 times 0.015 times 8 equals 3.6 Newton meter. Explain why torque falls linearly with speed in the unsaturated region. Use the torque speed equation T equals T stall minus open parenthesis T stall divided by omega no load close parenthesis omega, and discuss back EMF reducing armature voltage and current. Compare the torque expression for a shunt wound versus a series wound motor shunt. T equals KT phi fixed IS series. T equals KT KSI a squared flux proportional to IA. A motor runs at 1200 revolutions per minute delivering 2 kilowatts. What is its torque? Convert revolutions per minute to radians per second. Omega equals 1200 times 2 pi divided by 60 approximately 125.7 radians per second. T equals 2000 divided by 125.7 approximately 15.9 Newton meter.